All right, today we're going to tackle a concept that honestly powers a huge chunk of our modern digital world, and most of the time we don't even see it happening. We're diving into the secrets of stream computing.
I mean, really think about that for a second. You get that text message, right? The one about a suspicious charge, just moments after someone tries to use your card. How is that even possible? Your bank is dealing with millions, maybe tens of millions of transactions every single minute. There's no time to just sit back and collect all that data. The decision has to happen right now.
And that, right there, is the huge problem we're talking about. The sheer speed and amount of data coming from financial transactions or social media feeds or all those smart sensors out there, it's not a gentle stream. It's a full-on, high-pressure fire hose. And you can't just point a fire hose into a bucket and hope you can sort it all out later. It's just too much, too fast. So to handle this insane flood, you need a completely different kind of plumbing. And that's where the whole idea of stream computing comes into play. It's a new set of blueprints that forces us to completely rethink how we deal with data.
Okay, so think about the old way, traditional data processing. It's like filling up a giant lake with water, your data. And then, once the lake is nice and full, you send in your scientists to study it. Stream processing, it's the total opposite. You're analyzing the water as it's flying past you, grabbing the little bits of insight you need and just letting the rest of it go. It's all about processing data in motion.
Okay, so here's the deal, and this is absolutely crucial. The stream data model has some really strict rules. First, the data is a continuous, ordered sequence. Second, you only get one shot, one single look at each piece of data as it zips by. And the most important rule of all, you have very, very limited memory. You can't just save everything. And it's these constraints that forced all the incredible ingenuity we're about to get into.
All right, so let's get into our first line of defense. If you can't possibly process everything, how do you even start to make sense of the stream? Well, you need some really clever strategies right at the front door.
Yeah, this question really gets to the heart of it, right? How can you possibly understand the entire stream, like what's trending or what the average value is, without getting completely washed away by it? You can't drink the whole thing. So what do? The answer? You take a sip. Or, in technical terms, you use sampling. By intelligently grabbing a small random handful of data points as they fly by, you can actually build a pretty accurate picture of the entire stream. It's an estimation, for sure, but it's a super powerful and efficient way to understand broad trends, like, say, what percentage of people are clicking a new button on a website.
So sampling is awesome for the big picture, but what happens when you need specifics? Imagine you're a website trying to stop someone from voting twice in a poll. You need to know, for sure, if you've seen that specific user before. Sampling can't help you there, and you absolutely can't afford to store a massive list of every single user who's ever voted.
And this is where we meet one of the coolest, most elegant ideas in all of stream computing, the Bloom filter. The best way to think about it is like a super efficient but slightly forgetful doorman for your data. Okay, so here's how this genius doorman works. When a new user ID shows up, you run it through a few special math functions. Each function tells you to flip a specific switch in a long row of on/off switches. Now, when another user ID comes along, you check which switches it points to. If even one of those switches is off, you know for a fact, 100%, that this user is new. But if all the switches are already on, your doorman says, I've probably seen you before. And that's the beautiful trade-off. It never gets it wrong when something is new, but there's a tiny chance of a false positive. And for a lot of jobs, that's a perfect trade for saving a massive amount of memory.
Okay, so we can sip and we can filter. Now let's get into the really mind-bending stuff. These next algorithms honestly feel like magic tricks. They let us answer questions that just seem completely impossible given the rules we have to play by. So here's a classic problem, the count distinct problem. A big news website wants to know how many unique visitors they got in the last hour. Now the obvious way is to just store every single visitor's ID, right? But with millions of visitors an hour, that list gets gigantic, and we just don't have the memory for that.
I mean, the memory constraints we're talking about are just insane. It's like someone telling you to count every single person in a massive football stadium, but the only tool you have is a tiny sticky note. It just sounds impossible.
But believe it or not, it's not impossible, thanks to algorithms like Flajolet Martin.
Now, the math gets pretty deep, but the basic idea is just genius. It works by essentially turning every user ID into a long, random-looking string of zeros and ones. And the trick is, it only keeps track of one thing, the longest tail of zeros it's ever seen on any of those strings. See, the more unique users you get, the higher the odds that one of them will randomly generate a really long tail of zeros. It's kind of like a lottery. So by just remembering that one number, the longest tail, it can make an incredibly accurate guess about the total number of unique users. Just amazing.
But sometimes a total count isn't what you need. A lot of the time, what really matters is what's happening right now. A social media platform doesn't care about what was trending 2 days ago. It needs to know what's blowing up in the last 10 minutes. This means we have to count things only within a recent sliding window of time.
And for that, we have something called the DGIM algorithm. It's specifically designed to answer questions like, how many times did our network see a specific error in the last 15 minutes? And it does this with a really clever system of buckets. Think of it like this. The newest events go into small, very detailed buckets. As time goes on and those buckets get older, they start to merge together into bigger, slightly less detailed buckets. This lets the system keep a super accurate count of what just happened while it gracefully summarizes the older stuff, all without having to store every single thing from the last hour.
So, okay, we've got all these super clever, kind of magical algorithms. But this isn't just theory, right? Let's bring this all back to the real world and talk about why this matters so much.
Every single one of these things you see here, it's all powered by stream computing. That fraud alert text from your bank, the trending now list on your social media feed, the movie that a streaming service suggests the exact second you finish another one, or the security system that spots a hacker trying to break in as it's happening. None of this would be possible without the ability to analyze data on the fly. And that's really the big takeaway here. This whole idea of stream computing, it completely changes our relationship with data. It frees us from this old mentality of we have to hoard and store everything. We've figured out how to pull incredible value and make critical split-second decisions from information we might never even need to save.
Which, of course, leaves us with one last big thought. We started this off talking about data fire hoses, but really, we're heading towards entire data oceans. As everything from our cars to our coffee makers gets connected to the internet, the amount of data being generated is just going to explode. The principles of stream computing won't just be helpful, they're going to be absolutely essential. The only question is, what impossible problems will they let us solve next?